All right, let's dive right into this explainer and unpack something absolutely fascinating. Today, we're popping the hood on the abstract mathematical engine that powers OMI's peer-to-peer network discovery. Seriously, if you've ever found yourself wondering how these complex decentralized systems manage to keep track of massive amounts of information without completely falling apart, well, you're in exactly the right place. We're going to look at how the OMI Citation Resolver takes ancient mathematical concepts and literally translates them into cutting-edge network architecture. So the whole thing kicks off with a massive, very practical problem inherent to any decentralized architecture. How do peers actually discover missing data when there's no central boss to ask? I mean, in a traditional system, if you're missing a piece of the puzzle, it's easy. You just query the central server. The server knows everything, right? But in a true peer-to-peer network, no single entity possesses the entire semantic world. So how on earth do you securely and accurately recover missing network info when a global directory just doesn't exist? Now, you might expect the answer to be some massive, bloated routing table that everyone is constantly forced to update and share. But nope. To solve this, OMI does something brilliant. The unexpected answer actually lies in abstract algebra. Instead of relying on brute force network gossip, OMI taps into the deterministic computation patterns found in ancient algebraic structures to mathematically guarantee data discovery. It's relying on the undeniable, rock-solid laws of math. Let's start with the foundational piece of this algebraic puzzle, the Latin square. Simply put, this is a finite table filled with symbols in such a way that every symbol appears exactly once in each row and exactly once in each column. But a Latin square isn't just some fun Sudoku-style puzzle grid. In this context, it acts as a reversible finite resolver. It mathematically guarantees that if you have any two coordinates, you can deterministically recover the missing third. The core computational logic happening here is just phenomenal. Think about it. A row plus a column always uniquely resolves to a specific symbol. But because of the strict rules of the Latin square, the math works perfectly in reverse, too. If you've got the row and the symbol, boom, you can deduce the column. Have the column and the symbol, you can instantly recover the row. Any two knowns will always, flawlessly, determine the unknown third. Now, when we translate this pure math into OMI networking terms, things get incredibly powerful. OMI cleanly maps a row to an attestation, a column to an attribution, and the symbol to the discovered citation point. Think about the sheer power of this for a second. If a peer only has an attestation and a discovered point, they can instantly, locally compute that missing attribution without ever having to ping a central authority. It is completely deterministic recovery, a real game changer. Moving right along to Section 1, OMI's three-phase model. The system strictly operates in exactly three sequential steps. First up, declaration, which introduces the notation for the citation. Second is definition, which splits that citation into two complementary halves, an attestation and an attribution, basically giving it a bounded internal structure. Finally, discovery uses interpolation and interpretation to resolve positions. But here is the absolutely crucial takeaway. There is no fourth phase. OMI deliberately stops right there. It outputs an annotatable citation surface, leaving the actual application meaning and commands to be decided downstream by the user. It is totally outside of OMI's authority. Next up, Section 2, the power of quasi-groups. Now, you might be wondering, if we're leaning so heavily on algebra, why not just use standard algebraic groups to map all this out? Well, a traditional mathematical group requires some really strict rules. Closure, identity, inverses, and most heavily, global associativity. It demands a globally valid view of every single operation. But wait, OMI is peer-to-peer. Nobody has a global view. So instead, it leverages the quasi-group. Quasi-groups give you reversible local composition. They provide that deterministic recovery we need, but without the massive computational burden of requiring a globally associative view of the whole semantic world. And this beautifully illustrates the true peer-to-peer value. Declaration times definition equals the discovered point. Because OMI utilizes the highly localized rules of a quasi-group, if a peer on the network only possesses bounded table fragments, say just a declaration and a definition they grabbed from a neighbor, they can locally compute and discover the exact citation point. They don't need the whole network map. They just need their local fragments and this universal mathematical law. So, to manage all these fragments and intersections, OMI introduces a component called the Metatron scribe. Now, its role is not to command the system or alter authority, not at all. Instead, it acts as a faithful scribe of triples.
Utilizing what's known as a Steiner quasi-group rail, it interpolates missing endpoints purely based on that core algorithmic rule we've been talking about. Two knowns determine the third. It flawlessly preserves the resolver structure across the entire network.
Let's transition into Section 3, the bare metal, focusing on unisigns and 8 tuples. The absolute most important philosophical and architectural stance here is that OMI reads unary signs first. It treats numerical quantity and place value merely as later localized bindings. The 8-tuple actually begins purely as a unary relation of compatible signs that are type parallel, which just means they share a carrier type, even if they end up having different local meanings. And to guarantee exact zero approximation portability across completely different computers, it relies on strict hexadecimal nibbles as its local computational alphabet.
So what actually happens to those 8 signs? Well, in this system, pairing is relation, not compression. Instead of compressing these 8 signs down into smaller numerical quantities, OMI folds them into 4 pairs. For those of you familiar with programming history, you'll recognize this. It uses Lisp-style dot relations, specifically char, CDR, payload, and mask. These names literally declare how a position participates in a relation. It proves that the underlying tuple is highly structured, mapping out a current relation and its continuation, no matter how incredibly deep that recursive tail grows.
Bringing us to Section 4, the null ring and XOR balancing.
Okay, so when these compatible signs are finally lowered down to actual bit representations in a computer's memory, they're computed via a bitwise XOR operation. An arbitrary pair here doesn't have to produce a 0. Instead, it produces a reversible structural difference. And this difference is verified by these gauge witnesses, which are there to mathematically guarantee that the structure remains totally intact. Which leads us straight to this honestly beautiful concept, the null ring. Because of how the XOR operation works on these Lisp-style dot relations, when the complete relation path closes, it balances perfectly. Every shared boundary occurs exactly twice, and in XOR logic, anything that happens twice mathematically cancels out to 0. It literally does not matter how complex or convoluted the tail of the data structure gets, the complete relation balances flawlessly into the null ring.
So the ultimate takeaway really lands on this one crucial idea. OMI Canvas and OMI Workbook do not need to transport functions. They carry addressed relations. Think about what that actually means. The OMI network is fundamentally designed to portably carry pure structural mathematical relations rather than bound behaviors. The local machine gets to decide what to do with the data, sure, but the network simply and perfectly delivers the structural geometry of that data. I really want to leave you with this thought to explore today. If peers can perfectly map, transport, and recover missing knowledge simply by balancing algebraic geometry and localized equations, how many of our Internet central bosses are already completely obsolete? We've built an internet that relies on massive central servers to tell us what's true and where data lives. But if the math of quasi-groups and Latin squares allows peers to figure it out entirely on their own, what happens next? Thanks so much for joining me on this explainer. I hope this sparks some curiosity for you, and I'll catch you in the next one.